All right, so 5-1 was all about mid-segments. 5-2 was all about perpendicular bisector. What's the definition of a perpendicular bisector?
Line that bisects a segment at 90 degrees.
Good. Bisects segment N at 90 degrees. So it's perpendicular, meaning it's got the right angle. Bisector means it cuts the segment in half, right? And then we learned theorems based on the perpendicular bisector. So what's the perpendicular bisector theorem say?
That the endpoint is equidistant from the vertex.
So the point, any point that's on the perpendicular bisector is going to be equidistant from the endpoints. Yep. And the converse of that said that if a point was equidistant from the endpoints of a segment, then what?
It's on the perpendicular.
Good. Lies on the perpendicular bisector. So you need those for 1 and 2. 1 and 2 says to find AB, okay? 1 has two triangles. Well, you can cut it into 4 or 5, however you look at it, okay? But this segment here hits AC at its midpoint and is perpendicular to it. So that segment is a perpendicular bisector, which means that any point that lies on it is equidistant from the endpoints of this bisector. So what's true about 3x plus 1 and 4x minus 7? They're equal to each other. So you just have to do 3x plus 1 equals 4x minus 7. Subtract the 3x, add the 7. X is 8. But what's the question asking for? AB. So that's that segment here. What do I have to do? Take it, plug it back in. So 3 times 8 plus 1, 24 plus 1, which is 25. Alexis.
Like where it will give, but it's not actually.
No, it has to be. I mean, otherwise you don't have a perpendicular bisector. You can't do anything with it. Yeah. All right, so 2, same situation, just a different type of diagram. That ray here is definitely the perpendicular bisector of AC, which means B is equidistant from C and from A. So what's true about 5x plus 7 and 7x? They're equal to each other. Set them equal to each other. Subtract the 5x and divide by 2. And then again, this time it asks for AB. So what do I have to do with that 7 halves? Take it, plug it back in. And I'd get 49 over 2, which you can keep that way. Or 24 and a half, or 24.5, any of that would work. Questions on that one? Okay, so then 3 says the diagram, the perpendicular bisectors of A, B, C meet at point G. So what's that point called? The circumcenter. Good. So a point in which 3 lines meet is called a what? Any 3 lines. Do you remember what that's called? It's a point of concurrency. Okay? So the point where any 3 segments meet is called a point of concurrency. The point of concurrency of perpendicular bisectors is called the circumcenter. What's the theorem you learned about that? What's true about the circumcenter? It is equidistant from the vertices of the triangle, okay? So if I look at this little diagram, the first thing you got to figure out is which are my perpendicular bisectors, or which are the ones that are connecting that to the vertex, right? So give me the name of a perpendicular bisector. Evan. DG. What else? EG. What else? GF. All of those are perpendicular bisectors. Do you see that? Yes? Okay. So then if that's the case, then the segments that connect that circumcenter, which is G, to each of the vertices are all congruent. So AG is congruent to G, B is congruent to GC. Does that make sense? Yeah? So the directions say find EC and GC. So EC is here. If this is the perpendicular bisector, then what's true about EC? It's equal to BE. So EC is 5. And then it says find GC, which is here, which is the segment connecting the circumcenter to the vertices. So that would be equal to what? 7. It's equal to this, which is equal to this. questions on any of that? Okay, so again, takeaway from this section is what is a perpendicular bisector? What are the two theorems about a perpendicular bisector? What's it called where they meet, which is the circumcenter? And then what's the theorem about the circumcenter, which is that circumcenter is equidistant from the vertices of a triangle. All right, so chapter 5, section 3 is angle bisectors of a triangle. So in 5.1 we talked all about midsegments. In 5.2 we talked about perpendicular segments, or perpendicular bisectors, sorry. In 5.3, angle bisectors. It's a lot of different stuff. But my advice on this chapter is make yourself almost like an outline. Start a note of notability. That's chapter 5. Start with 5.1. Do the definition of a midsegment. Give yourself a picture. And then write out the theorems that you're supposed to know about the midsegment. Then go to 5.2. Do the definition of a perpendicular bisector. Give yourself a picture of it. And then write the theorems that apply to that. The theorems that apply to the circumcenter. And then we'd add 5.3, which is angle bisectors. So if you want a good review as you're building, that would be my recommendation. Okay? So the angle bisector, which we already know what an angle bisector is, right? It's something that bisects an angle. The angle bisector theorem says if a point is on the bisector of an angle, then it's equidistant from the two sides of the angle. All right, so one of the most important parts of this is identifying what they mean by the distance from that point to the sides of an angle. So if I'm standing on one side of a river and somebody else is on the other side of the river, how do I know what's the shortest distance between us? How do you measure the shortest distance between 2 points? It has to be a straight line, which means what? How do you know it's a straight line? Like if I have two things here and I'm standing here, is the distance between these two? No. The distance between these two? Why? What does straight mean?
It's not like diagonal.
It's not a diagonal. Perpendicular, yes? So the shortest distance between two lines is the perpendicular segment that connects them. That's true distance. So if you notice in this diagram, in order to show the distance from a point on an angle to the sides, those segments have to be perpendicular. So I can't say that from D to this point here is equidistant from that point. Those are not the same things, okay? That's not distance from that point to the sides. In order to show that the distances are the same, you have to draw a perpendicular segment. So one that hits the side at a right angle. If it lies on the angle bisector, then those two segments are going to be equal. So in this case, if ray AD bisects angle BAC, and DB is perpendicular to AB, and DC is perpendicular to AC, then DB equals DC. So these two segments would be equal. The converse to that, switch the if and the then. If a point's in the interior of the angle, so it's got to be in between the two sides, and it's equidistant from the sides of the angle, then it lies on the bisector of the angle. So if you look at the diagram that's there, does D lie in the interior of angle BAC? Yes, that's the first thing it's got to be. Is D equidistant from the sides of angle BAC? So it's got the right angle showing that it's true distance, and it's got the little congruency marks showing that those two segments are congruent. If both of those are true, then I know that D lies on the angle bisector. In this case, AD is the bisector of angle BAC. So it's the exact reverse or converse to the angle bisector theorem. Okay, concurrency of angle bisectors of a triangle. So just like a perpendicular bisector, there are 3 angle bisectors to every triangle. And where they meet, that point of concurrency would be equidistant from the sides of the triangle. So perpendicular bisectors are equidistant from the vertices. Angle bisectors are equidistant from the sides. So this time my angle bisectors would be like these, the red ones. And you'd know they're angle bisectors by something like that. They'd be marked as congruent, or it would say it, that AP is the angle bisector, BP is the angle bisector, CP is the angle bisector. And then all these little segments that hit the side at a right angle are going to be congruent. So EP would equal PD would equal PF. All the little blue segments in this one. Okay, that point of concurrency also has a name for angle bisectors. This time it's called in-center. So in-center is the point of concurrency of the three angle bisectors of a triangle. And they always lie inside the triangle. So if you remember, perpendicular bisectors could either lie, the point of concurrency could either lie in, on, or outside the triangle, depending on the type of triangle. The in-center is always inside. So think in, center, inside. It's always inside, no matter if that triangle is a acute triangle, an obtuse triangle, or a right triangle. So this little picture, okay, each of these would be your angle bisectors, angle bisector, angle bisector, okay. Where they meet, this point is your in-center. And then this diagram just added that circle in. That circle is going to have a radius of whatever the distance is from the in-center to the side. And it would go all the way around it, okay. So a new vocab term for you guys is inscribed. This circle is said to be inscribed within the triangle. You can reverse it, like if I had a triangle inside a circle, I would now say that the triangle is inscribed within the triangle. So whichever one's on the inside is called inscribed. This says in exercise, oh, this is just one. You'll see it on the next slide. Find the value of x. So what are those 27 degrees telling you? Why are they there? Showing that the two angles are equal, which means what? That ray is the angle bisector. If it's the angle bisector, then x and 15 are going to be the same. X is 15. Okay, same set of instructions. Now, what piece of information are you given? You have the perpendicular segment, right? So I know that it's distance, and then what? What other piece of information did they give you that you needed? They're congruent. Those two segments are congruent. So if the distance, right, if a point on a line is, or in this case a ray, is equidistant from the sides of the triangle, then what's true about that ray? It bisects that angle, which tells you they're equal. So 3x plus 5 is equal to 4x minus 6. And then subtract the 3 and add the 6. Yep.
What are those two equations?
What are they? Like what do they represent? The angle in here. So what if I had asked you for the value, let's say this is angle A, B, C. What if I asked you for the value of that angle? How could you find it? Take the 11, plug it back in, right? And then what? And then double it, or add the two together, right? Does that make sense? Yeah, okay. Okay, last one. In the exercise, again, find the value of x. So this time I know what about the angle? It's being bisected, and then those little segments are showing you the distance between the angle bisector and the sides, which should be equal 5x should equal 6x minus 5. So I'd get negative x equals negative 5, and x would equal 5. So again, my advice is to do like a running outline. I would start with 5.1, which was the mid segments. I would give myself a picture of the definition and the theorem. And then 5.2, which was the perpendicular bisectors. Same thing, I would do the definition, the theorem, the converse, and then the point of concurrency, which is called the circumcenter. And then the circumcenter theorem. And then I would now add to it 5.3, which is the angle bisector. I would do the definition, give myself a picture, do the theorem of the angle bisector, okay? This one has an in-center and a theorem about the in-center. It's going to be a lot of information, and because we're just going to keep adding to it, you don't want to get behind on it, okay? You want to be able to differentiate these with a picture, okay, and with the definition. Okay, so given plane P is perpendicular bisector of x, z at y. So perpendicular bisector tells you that it hits it at its midpoint, so x, y is equal to y, z, and that it's perpendicular. So I could have said that y, w is perpendicular to x, z. Both of those are the definition of a perpendicular bisector. Okay, so I'm trying to get the A is that x, w, which is this segment, is congruent to ZW, which is this segment. So let me zoom in a little bit so that you can kind of get an idea of what you're looking for. So because we just came off of congruent triangles, I would assume it's probably trying to get to you to go that way. If that's the case, I already have that x, y is congruent to y, z, right? So I've got one pair of sides congruent. And then I've got x, y, or xz actually, is perpendicular to yw, which tells you that there's a right angle here, and there's also a right angle here. So you can say something like angle xyw is congruent to angle wyz, and that's because perpendicular lines form congruent adjacent angles. And then state the obvious about these triangles. So what piece of the triangle are shared? That reflexive side, that YW, right? Oh, that's what my space is. So YW equals YW. Y. No, it's YW. For the two triangles that are here. So I'm trying to prove color. I'm trying to prove this triangle is congruent to this triangle. So there's one above the plane and there's one below the plane, if you kind of look at it that way. Like a triangle sitting on top of a piece of paper and another one sitting underneath it. Okay, so now I've got two, this is reflexive, and then I've got two triangles that are congruent. X, Y, W is congruent to Z, Y, W, and the reason is side, angle, side. Got two pairs of congruent sides in the included angle. So if that's the case, then I can do that first step, the first A. which is xv is equal to z, xw.
That's only A.
That's A, yeah. It said it was equidistant. Yeah, you could do it that way. Yeah. Then B. Wait, what?
Did you give us something like this?
No, it's like 17 steps. I'm not that mean. All right, so now can I go on? Yeah? Okay, so then B is that XV, which is this segment all the way on the outside, is congruent to ZW. So there's a triangle on the bottom right and there's a triangle on the top left, okay, which are both right angles. So you've got your congruent angles. And then you've got your congruent segments, because I'm not going to go through it all, but perpendicular bisector theorem gives you that congruent segment, because those points would be equidistant. And then the side that's already marked as congruent. From there, you can go to CPCTC. And then the last thing you're trying to prove is triangle VXW. VXW, which is this angle at the top, and VZW at the bottom. So for those, you have another reflexive side, and then you already have the two sides that we marked as congruent. Those triangles would be congruent to the side, and then CPCTC. So you'd probably, I mean, if anything, you'd get like one of those. You're going to get all three of those in one. Okay. And I'll tell you, I tend to stay away from three-dimensional pictures on proofs just because they're super hard to see, and they're also super hard to make. So I'm not saying you'll never get them, but odds are usually that I don't like making them. They're hard to make, and they're hard to see. Okay, that's when your color coding comes really in handy. Okay, if I can't give you a colored test, I have a hard time doing three-dimensional just because you can't see it. Like when we get to pyramids and all that stuff, you're gonna have to, but for this kind of stuff, no.